Hi, and welcome back to another week of extreme value theory. In this final week of the course, we're going to focus in on financial applications of extremes. In this first lecture, we're going to consider the Hill estimator, which is applicable only to heavy-tailed data. So in lots of the environmental applications that we saw earlier in the course, we ended up with a negative or zero estimate for our shape parameter psi. And this often occurs in environmental applications because physical limitations on the process being studied mean that events can't become very, very large. In lots of financial applications, these physical limitations are removed, however, and it's very common to see heavy tails when modeling financial data. When we end up with heavy-tailed distributions for our extreme values, so when psi is greater than naught, we've got a useful approximation that we can use for our limit distribution with a much simpler form than the GEV or the GPD. Specifically, for large values of u, our tail begins to look like an inverse power law. So the survivor function, 1 minus f of x, which is the probability that x is greater than little x, can be approximated very well by some constant c divided by x to the alpha, where c and alpha take positive values and x is bigger than some large value u. So this can be thought of as an approximation to our GPD. And as you can see, the form of this is much simpler than our GPD density. And so that's going to simplify our modeling process here. But it's important that this approximation only holds when you have heavy-tailed data, so when psi is greater than naught. And in this case, if we're looking for some correspondence between the parameters in each different setting, then the parameter alpha here is equal to 1 over the shape parameter psi. So what are some benefits of using this approximation? Firstly, we saw just before that the expression that we're using in our modeling process is much simpler, both in terms of the complexity of the expression itself and also in terms of the number of degrees of freedom we have. So in this approximate version, we only have 2 free parameters, which we're going to estimate. Whereas in a GEV model or a GPD, we have 3 if we're including the rate parameter here. And that's important because although using this approximation we can separate out the shape parameter, it's not possible to separate the GEV components or the rate and the scale component of the GPD. And this approximation was particularly important in the days before numerical optimization was a widely and easily available tool, because nowadays we can easily use numerical methods to optimize the GPD likelihood, but before that was an option, we had to make this simplifying assumption in order to get tractable results. A third benefit is that if we skip back here, what we have is an approximate relationship that is about x itself, whereas when we're considering the GPD, we're looking at x conditional on it being large. What this means is that when we are interpreting our results, we don't need to undo the conditioning. And finally, since this approximation is very good for large values of u, and financial applications often have heavy tails, this approximation is still commonly used in financial applications, even though the numerical methods for the GPD are commonly available. So how do we go about estimating the parameters in this approximate model? To estimate alpha, what we can do is differentiate our approximate form for the CDF to find this form for the probability density function. It's approximately equal to alpha times u to the alpha times x to the minus alpha minus 1. And this is going to be valid for large values of x. So if we use this approximate density function and let nu represent the number of exceedances of some high value u, then this is going to lead to a maximum likelihood estimate for alpha being given by this expression. So it's the reciprocal of the sample mean over the values that exceed u of the log of that value minus the log of u. When we're calculating this, we have to pick u, making very similar compromises to when we're doing GPD type modeling. So we have a bias variance trade-off about how much data we're including in our analysis. A pragmatic way of choosing this is similar to the R-largest approach, and it's to choose u to be equal to the kth largest order statistic in our sample, in which case this sum is going to be over k terms. In terms of estimating the parameter c, then our survivor function under this approximation, so 1 minus the CDF, is going to be given by c over u to the alpha. And what we can do in order to estimate c here is to equate the empirical and model proportions of values that exceed the threshold u. What this ends up with is a natural point estimate for c, which is given by the number of exceedances of u divided by the total number of observations n, multiplied by u to our estimate of alpha hat that we obtained earlier. And what these parameters do is give us a way to estimate high quantiles of f without using numerical routines, and also without having to undo that conditioning like we do for the GPD. So the p return level here, x hat p, can be estimated as p over our estimate of c, all raised to the power of -1 over our estimate of alpha. And what this is going to be useful for is estimating things such as return levels, the value at risk, and the expected shortfall without having to resort to these numerical routines. So, in summary, what we've introduced in this video is the idea that in financial applications, heavy tails are very common, and because of this, we can often make a simplifying approximation of the extreme value distribution. What this allows us to do is avoid the need for numerical optimization and get easily tractable results for quantities such as return levels. What we'll look at next time is linking these into specific financial metrics such as the value at risk and the expected shortfall, and see how those link into the more general forms of extreme value analysis that we've introduced in the course up to now. And in the final lecture, what we'll be looking at is extending beyond univariate extremes to see how we can describe the relationships between two processes at extreme levels. Thank you, and I'll see you in the next video.